Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, Basics, Sign of Trigonometric Functions, Concept number 11, Quadrant 4, and the reference angle. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is so effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2. If I could stick every math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I would. So inbox me at memedicine@gmail.com to get your healthy dose. You have lots of peers, classmates, friends, and or colleagues who could use a boost in Algebra 2 as well. So tell them to inbox me at memedicine@gmail.com so that they too can benefit from this cram session. You'll be glad you spread the word because they'll make great study buddies. And last but not least, cramming often has a negative connotation. But what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive. We're not hurrying, we're cramming. There's a difference. Hurrying is jam-packing tons and tons of unorganized information into a tiny amount of time, okay? Whereas cramming is taking quantum leaps in your understanding in an organized way, not unorganized, in what seems to be a very tiny instant. Or instance rather, let's jump into the concept of quadrant 4 and the reference angle. Standard position and reference angles. What is the reference angle 𝜃𝑟𝑒𝑓 for an obtuse angle theta located in quadrant 4? I'll give you a moment to think and definitely press pause if you need to. All right, so hopefully by now you were able to arrive at an answer, and if not, that's completely fine. Before we get into the reference angle located in quadrant 4, we need to properly differentiate between the concept of 𝜃𝑟𝑒𝑓, the reference angle, in each quadrant because the signs of trigonometric values depend on the x and y sign in the quadrant in which the terminal side of 𝜃𝑟𝑒𝑓 is found, okay? And in order to understand the concept of 𝜃𝑟𝑒𝑓 in quadrant 4, we first have to organize the concept of standard position in quadrant 1. So we need to establish this bad boy here in your mind, okay? And an angle in standard position in quadrant 1 has 6 key features. First, an angle theta in standard position has its vertex located at the origin. The initial side ray is located on the positive x-axis, and the other ray terminates in quadrant 1, okay? This is called the terminal side ray, but we'll be cute and call it R for short, R short for ray, okay? And let's say that we arbitrarily choose a point here. And we're going to call our point P, P short for point, and this point has x and y as its x and y coordinates on this Cartesian coordinate plane, okay? So I think these are pretty basic concepts that shouldn't be mind-boggling so far. But for our purposes, we're going to highlight the coordinates of P, and we're going to say that this ray, which is no longer a ray, rather it's a line segment, goes to the extent of x, which P established, and it rises to the level of y, which was also established by assigning this arbitrary point P, okay? And what's really neat is that we now have the formation of a right triangle, okay? So yeah, I think you're with me so far. I mean, if I can get this, trust me, you can get this. And this P here just basically set us up for some really good things, because this triangle, when we're dealing with our XY Cartesian coordinate plane, is what we base all the trigonometric functions for triangles that we calculate, such as sine, cosine, inverse sine, cosecant, you name it, okay? All right, so a takeaway point that I really want you to understand is that because the extent of r goes to x, x is a coordinate, as shown here, so x can be positive if the ray segment ended in quadrant 1 or quadrant 4, but negative if this terminal side ray was in quadrant 2 or 3. But it's going to be positive in our case because here we're dealing with quadrant 4, okay? And the same goes for y. Y is positive in quadrants 1 and 2, but negative in quadrants 3 and 4. And for our purposes, this y is going to be negative because eventually we're going to be dealing with quadrant 4, okay? But the ray, or the segment, the newly formed line segment established by point P, or the hypotenuse of a triangle opposite the 90-degree angle, that's always going to be positive. And the reason is it's not a coordinate point, it's actually a measurement of length. So we'll just establish this here. R, which is short for our ray, is equivalent to the square root of x squared plus y squared. And this is just a play on the distance formula. That's why it's so cool that the vertex is located at the origin, because the coordinate here is 0, 0. So basically we have x minus 0 squared plus y minus 0 squared. That's why this is a play on the distance formula, which can never be negative. That's the reason why you square the x's and y's, and you undo the squaring by taking the square root. What this essentially does, squaring and then taking the square root, is it gets rid of any negatives, leaving you with a positive measurement value, okay? So again, this is a measurement of segment length, and it's always positive. But our x and y's can be negative or positive. Okay, I think you got that. Thus, our theta reference here is always going to be equal to theta. This is our theta reference. It's an acute angle, and the reason why it's acute is because it's bound between the quadrantal angles 0 degrees and 90 degrees. I can't say quadrantal. Quadrantal angles are all the angles whose terminal side rays end on either the x-axis or y-axis. So we'll just run through a few. 0 degrees, the quadrantal angle 90 degrees, the quadrantal angle 180, the quadrantal angle 270 degrees, and the quadrantal angle 360 degrees, okay? But here, our theta, which is theta reference for quadrant 1, and basically for all the quadrants, you'll see why in a few moments, is always an acute angle, a positive acute angle, okay? And the reason why theta reference is so important is because when you're calculating inverse trigonometric functions using your graphing or scientific calculator, what you're going to get for an answer, if you do like the inverse sine, inverse cosine, inverse tangent, is going to be the reference angle. So you would need to determine which quadrant you're in, okay, to see whether or not you'll have to manipulate this answer to get your answer of interest. So it's a really important point to highlight because a lot of people have told me that they lose points for this one little step. So we said that this angle is acute, but anything beyond 90 degrees is obtuse. And we're in quadrant 4, that's where we want to end up. And so for any obtuse angle, okay, this is definitely an obtuse angle, in quadrant 4, theta reference is also going to be the positive acute angle made with the x-axis. It's just that instead of being here in quadrant 1, what we did was a horizontal flip, about the y-axis, okay? All right, so I think that pretty much sums it up. But then if we're not interested in theta ref, let's say we calculate theta reference for our inverse sine function and we get like 45 degrees. Or you know what, my adding and subtracting skills aren't on point today, so let's just say theta reference is 20 degrees. But that's not what we're interested in. We're interested in theta. Well, what you would have to do is figure out what your theta is. If you want to find theta reference, you can subtract theta from 360 degrees if you're in quadrant 4, okay? This is a theta reference formula for quadrant 4 only. But if you want to know theta, this big guy right here, our obtuse angle, what you're going to do is subtract theta reference from 360 degrees. So for example's sake, if we were to subtract our 20 degrees, pretend theta reference or theta sub ref, from 360 degrees, our actual obtuse theta would be 340 degrees. Okay? All right. So intellectual comprehension of all this material is not difficult. And after the short amount of time it takes to complete the entire Cram session series, you'll be prepared to answer a battery of questions about Algebra 2 concepts, okay? So definitely inbox me at memedicine@gmail.com to order the complete Algebra 2 Cram session. Thanks for tuning in.